All right, let's get started. Can people in the back hear me? Yes? Okay, good. So first I want to tie up some loose ends from the last lecture, because I'm sure you're all dying to know what the solution is to this puzzle. You can sleep. Yes, yes. So if you want to solve this yourself, it might be a good time to plug your ears, don't look, put some heavy metal on, I don't know. But if you want to know what the solution is, you start by taking these right turns only. That will take you this way to the other side. Okay, so you made it to the other side, that's good. You're still taking right turns. And now you pass the squiggle, so now you go from right turn only to left turn only taking. Now that was unexpected. The only way to solve this puzzle is if you go back to the right-hand side, because that puts you in the right position where you pass the squiggle again and finish it with a right-hand turn. Now the only reason why I want to show you a puzzle like this is that it's an example of hill climbing, where an obvious strategy to solve a puzzle like this is to try to get closer to the goal, right? It's a very simple, sensible strategy. But occasionally you might get stuck using hill climbing strategy, because what you need to do is often move away from the goal, move further away from the goal in order to solve it. So this is an example of where you can get mentally stuck because of a local maximum. Okay, but today we'll switch topics and talk about language, mostly about speech perception. And actually I think I'll keep this whole lecture a little short and skip the whole bit on semantics at the end. All right, so there are many levels of language, and each of these levels is associated with a whole field in linguistics, people that exclusively study sort of one aspect of language. Language is generally a huge topic in psychology. So one level, the level that we'll talk most about today, is phonology. So this is the study of the sounds in a language, which sounds are used in a language, which are the phonemes that make up a language, that produce sort of meaningful differences in a language, and which ones are the, which is acoustic variability that doesn't map onto sort of meaningful differences. Now, phonology is both about the production of language as well as the perception of language. Now, another level is morphology and semantics. So how do we attribute meaning to small elements of language, like morphemes or words, and how do we put meaning together when we form sentences? Prosody is very important. So it's not just a choice of words that convey meaning, it's all the other nonverbal stuff, your gestures, and how you say something is very important to create meaning. A huge field in linguistics is syntax. We won't talk very much about syntax. The book talks a little bit about syntax. Basically, what are the rules for combining words in a sentence, and how does it affect meaning? And finally, pragmatics. We also won't talk about that. How is language actually used in practice? So there's the thing that you actually said, and there's the thing that the person at the other end perceives or infers. And oftentimes we go well beyond the specific words that are mentioned in the context. We use our background knowledge, our general knowledge, to infer sort of the meaning or intention of an utterance. So, oh, this is old. Let me see. All right. Okay, so with prosody, prosody is about the melody that's used when constructing sounds, and the intonation pattern. And clearly that has an influence on the meaning of an utterance. So you can have declarative statements like "you are going home," interrogative statements, "you are going home," where the voice is rising at the end of a sentence, or imperative statements, "you are going home," right? Clearly a different intonation, and that has consequences for the meaning of an utterance. The prosody also can carry information about the emotional state of a speaker. So we did some research a couple of years ago where we looked at couples that come in for marriage counseling, and we try to understand how healthy people's marriage is based on what people say and how they say it. And it turns out that how you talk to each other, perhaps not surprisingly, is a good indicator for how healthy your relationship is. So there was one sentence that popped up quite a bit in marriage counseling. "You made a big deal about it." So I want to show you all kinds of utterances. And it clearly vary in terms of emotional state and the prosody, essentially.
You made a big deal about it. 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 You made a big deal about it.
So it sounds like accusing the person a little bit. You made a big deal about it, and sometimes it just carries a little bit more weight than other times. And analyzing prosody is very important to understand the emotional state of a person. Okay, so moving to phonology, and I think for the rest we'll stick to phonology. So this is the study of sound patterns of a language. The smallest unit is a phoneme. So this is the unit of sound that can be altered and change the meaning of a word. So all these words listed here in English, gin, kin, pin, tin, win, they have different meaning. And because they have different meaning, the initial sounds, they must be associated with different phonemes. Right? So the g, the k, p, all these consonants are meaningful phonetic contrasts in English. In English there's about, I think there's about 36 different phonemes. There's a debate on how you count phonemes. Most languages have about 40 to 50 different phonemes. And different languages have different phonemes, right? Different sort of sets of phonemes that lead to sort of meaningful differences in those languages. Now, how do we go from phonemes to speech perception? So this is an incredibly complicated process. And one important aspect of speech perception is that it operates in a hierarchical fashion. So there are different stages of processing where you put lower level units together to form higher level units. So in one stage, you as a person doing speech perception, in your mind you are detecting individual phonemes. Right? It's a b, t, r sound. And then you combine these individual phonemes into higher level units. There's some debate about what the higher level units are. Are those morphemes, syllables, something else? But there's a sense in which you put higher things together. Ultimately, you form words. And then once you have words, you retrieve word meaning from memory and put sort of the meaning of a sentence together. So there's clearly a hierarchical organization in speech perception. The other important aspect of speech perception is that it's interactive. Another way to say that is that it has a top-down organization in addition to a bottom-up organization. So you're not just going from one stage to another stage in one direction. It's highly interactive. You can do speech perception sort of in multiple directions at once. While you are detecting individual phonemes, simultaneously you might be detecting words that would make sense from those individual phonemes. And that analysis of the words can have an effect on the detection of the phonemes that make up that word. And you might in fact use any other information that you have available, like the person's gestures, lip movements, we'll talk about that, to understand the utterance. So it's it's hierarchical as well as interactive. Now, one of the big puzzles in speech perception is how you even detect individual words. It seems so effortless how we can parse an utterance into individual words. And we have this sense that we're detecting these discrete units. But why this is remarkable is that this subjective sense of having these discrete units, words, that doesn't show up in the raw signal at all. If you look at the acoustic waveform, there are no obvious pauses between words. And one way to visualize that is to look at this spectrogram. So a spectrogram is a visualization of the various, the intensities of various frequencies at different points in time. So in a spectrogram you have time running horizontally, you have frequency going vertically, and the color, the darker the color, the more intensity there is of that frequency or pitch at that particular time. Now these spectrograms, they reveal a lot of interesting patterns. One pattern is you see these stripes, right, running horizontally, and those are called formants. And for any speech pattern, there are multiple formants at the same time. So there's different sort of frequencies that are operating for sounds, and those correspond to different resonating frequencies in your vocal cord. A male speaker, right, with a lower pitch has lower formants than a female speaker. And so this pattern of stripes is very indicative of the type of speaker. But for the purpose of this slide, you don't see any white bands running all the way vertically. You don't see any time when there's no energy at a particular frequency. There seems to be, when you have a sentence like I owe you a yo-yo, there's always some energy at some frequency. There are no pauses. So obviously at the end of an utterance, when somebody stops speaking, there is a pause. And that is useful to learn about, breaks between words and what words are. But pauses occur pretty rarely. Now, to give you a sense of how difficult it is to hear individual words, you have to go to a foreign language. So I went to Finnish here in the hope that nobody speaks Finnish. Is that fair? Does anybody speak Finnish here? Good, okay, because I'm not quite sure about the translation and whether that's correct. So I'll show you play some sound clips, and the only thing you have to do is to give an estimate of how many words there are in in each of these utterances. Okay, let's start with the first one.
Hyvää huomenta.
How many words do you think there are?
Hyvää huomenta.
5. Somebody says 5. Somebody says 2. Okay. So there were actually 2 words. And it means good morning. Okay. Now this one.
Kiitoksia oikein paljon.
All right, and again.
Kiitoksia oikein paljon.
So here are 3 words. It means thank you, apparently. I hope. Hope that's what it means. Okay, now the difficult one.
Ilmatyyny-alukseni on täynnä ankeriaita.
Sounds pretty foreign. Say it again.
Ilmatyyny-alukseni on täynnä ankeriaita.
1. Well, you can see where I'm going with this. There were only 4 words in there. That doesn't seem right, but it's only 4 words. Now, apparently this message means my hovercraft is full of eels. This is a joke from Monty Python. There's a scene where a person tries to translate from Hungarian into English, but screws up and then ends up with these nonsensical sentences like, my hovercraft is full of eels. But the point is, yeah, we have trouble sort of understanding individual words when it's a new language, right? And this process of detecting word boundaries, this is the exact problem that infants are facing when they're trying to listen to you and understanding what you as a parent are saying to them. They can't use natural pauses as a cue. They have to do something else. Okay, so there's two big problems in speech perception. One problem we just mentioned, that words are not neatly segmented. There are some pauses, but not that many. The other problem is that phonemes, they're not associated with the same acoustic pattern. They're not invariant. You can't sort of point to some frequency signature and say, that's this phoneme, and this is the pattern from this phoneme. And the reason is that the way you articulate a phoneme depends on the previous phoneme. And also, it depends on the phoneme you're going to pronounce next. And this relates to the phenomenon of co-articulation. Because of the constraints of our articulatory system, you can't sort of quickly move your, let's say, your tongue from one position to another position. It takes time for your tongue to move. And because of that slowness of your articulatory system, you're blending together various sounds, right? As you're pronouncing one thing, you're still sort of pronouncing the sounds of the previous thing that you're trying to say. And that means that there is no one pattern associated with a phoneme. It's highly context dependent. On top of that, there's many speaker differences. The exact frequency pattern of a phoneme depends on age, it depends on sex, it depends on dialects, talking speeds, etc. So it's nothing short of a miracle that Siri on your iPhone can even understand what you're saying. Right? It's only the last couple of years ago that computers are trying to, can really understand human speech. So here's a visualization of co-articulation using a spectrogram. So if we have the two phonemes d and as in dumb, then there is some pattern of frequencies associated with d. There's a pattern of frequencies associated with and there's clearly different energy at these different frequencies. But as you progress from one phoneme to another, things start to blend, where in between the d and the you have frequency characteristics that are blending both phonemes. So, and then this is constantly happening as you move from phoneme to phoneme. Now, so the question is, how then, what are some tools that we use to deal with this massive variability in input? Right? If things can be pronounced in so many different ways, how can you map it onto sort of categories that we understand that are meaningful to us? So we'll talk about three phenomena. One is that we use our semantic and lexical context to influence our speech perception. So we'll talk about phonemic restoration effect. We also use visual cues, much more so than we think. So when you look at somebody's lips while you're listening to them, that has actually a great contribution on the level of understanding you get from what somebody's saying. And finally, we'll talk about categorical perception, what you know about words, what you know about phonetic contrasts around the world, that influences your perception of individual phonemes. What you know about sounds can actually warp your sensation of sounds. So first, phonemic restoration. So if I play you this sound.
Legislature.
Okay, and now I inject some noise somewhere in the word. Let's say that the noise could be somebody coughing, or in this particular case, you actually erase, part of the time window, and you inject actually some noise. You replace it with some noise.
Legislature. Legislature.
Now in this case, the S sound was replaced with noise. But what do you hear?
Legislature.
Oh, sorry, that was the wrong one. That was that's confusing.
Legislature.
Do you hear the S? Oops.
Legislature.
So that's remarkable, right? The S is actually not in the raw signal. It's simply not there. It was replaced by noise. But you might be hearing it, and for some people that effect is stronger than others. The only reason you could hear that sound is if there's some top-down influence of some higher level unit on a lower level unit. You know that's the word legislature. That's obvious from the context. And that is affecting the way you process and perceive those individual sounds. So speech perception does not go one way from lower level units to higher level units. It flows both ways, right? So sometimes you can make up sounds that are not there. But there's a limit to what you make up. So if I play you this.
Legislature. Legislature. Legislature.
So here I just inserted a pause as opposed to a noise. And here most people don't hear the S, right? It's not plausible that an S could have been obscured by noise here. There was simply nothing there. Now there's other experiments that show that this phonemic restoration, in other words, how you can repair phonemes from very noisy inputs, that can happen with fairly long distances and based on semantic context. So if I play you this.
It was found that the peel was on the axle. It was found that the peel was on the axle. And
when you ask people, what did you hear? They will report wheel, right? If this sound is played.
It was found that the peel was on the shoe.
And again, you ask people, what did you hear? They say they hear the word heel. Yeah, I don't find this demonstration all that compelling. Maybe you know that it should be the word heel. Maybe you didn't quite hear it. But according to these researchers, phonemic restoration can happen sort of on various time scales. And for some people, they really seem to hear those sounds that would make the most sense given the current context. Now, how many of you have already heard about the McGurk effect? So, small number of you, okay. So this is a demonstration showing that your speech perception is guided not only by the sounds that you hear, but also by visual cues. For example, the lip movements of the speaker you're listening to. So let's look carefully at what this person is saying. Okay, so when you look at this person, what is this person saying? It's not a word, right? It's just a sound. What do you hear? I'll play it one more time. Okay, so is it fair to say that most of you will hear da da? No? Yes? Now, I'll play it again, but now you don't look at the screen, right? So now you don't get the visual cues, and let's see if that changes your perception. So if you go back and forth, looking versus not looking, does that change? So you get a sense of this strange, it's almost an illusion of some kind. So what's going on here? This video is doctored. There's the sound of the speaker, and the lips make actually a different movement than the one that's naturally associated with the sound. So the lips actually make the movement ga. So some of you said ga, which is pretty good. You're good lip readers. The speech sound is actually ba. Ba, ba, ba. And again, this is doctored, right? So you just superimpose the lip movements of ga with the sound of ba. And for most people, that leads to perception of da. So this shows that speech perception doesn't not just use the sound, it uses all these other cues like the lip movements and all the, perhaps nonverbal cues, gestures as well. So clearly the brain is trying to fuse different sources of information to make sense of the information. Here's another one. You might not know this one. This is computer generated. Now listen to what, if you look at the screen versus not look at the screen, there should be a difference that you hear.
My dad taught me to drive. My dad taught me to drive. My dad taught me to drive. My dad taught me to drive.
Does anybody have a sense of what the two messages are? My dad taught me to drive and bribe. Yeah, that was the bribe versus drive, yes. This one doesn't seem as strong to me. Again, this is one of those doctored videos. All right. So speech perception is highly interactive. One level can influence another level of processing. And whenever your conceptual knowledge, your very high level knowledge of the world influences your perception of sounds or images, when we deal with visual stimuli, then you can have a phenomenon called categorical perception, where your perception of physical differences in the world gets warped by your knowledge of the physical world. And people with different conceptual knowledge would warp things differently, would have different perception of sounds. So here's an illustration of this phenomenon. There are real differences, physical differences out there in the world. Let's say there might be two types of chicken. And when you look at these two types of chicken, two different categories, because of your knowledge that these are two different categories, you might amplify the differences, the physical differences between categories, and you might actually minimize the physical differences within categories. So that's categorical perception. But those differences, so those are in your mind, right? The real physical world and what the differences are might be very different from your perceived differences between categories and within categories. So let's give an example of some very simple stimuli where your perception of the sound or your knowledge that there are different sound categories influences your perception. So here there's a sound and so there's da and ta. Now these are computer generated, and you can actually smoothly interpolate between these two sounds, the da sound and the ta sound. And I'll show you this interpolation. So da Okay, so you go from one sound to the other by doing one simple change. And that change is shown here in this diagram, so that you don't have to know the details of how these stimuli are constructed, but what's changed is the so-called voice onset time. So when you pronounce ta, it takes a little bit longer before your vocal cords, when they start to vibrate, when they are voicing, when the voicing starts. And with da, the voicing starts almost immediately. So as you go in this construction from da to da, you just increase voice onset time. Now here's one way to demonstrate categorical perception, that continuous differences in the world and sort of equal sort of distances in the physical world, they're not mapped to sort of equal distances in the mental world. So this graph shows you the transition of the da to the ta sound by just slowly increasing voice onset time. And when you ask people what sound do you hear, da or ta, you see a sharp discontinuity somewhere along this line. So most people would say, yeah, a da is a da. But when you get to these more ambiguous situations, people quickly flip over to the other side. So you have this very sharp discontinuity in identification. So it's not like linear, where small differences are constantly leading to a difference in identification. You have this very sharp boundary. Also, people are a little bit slower to identify sounds that straddle the category boundary. Right? It takes a little bit longer to identify this ambiguous da-ta sound than sounds that are more clearly da or ta. Now here's the key aspect of categorical perception. So if I play you these two sounds and I ask you, are these two sounds the same or different? Oops. Does that sound the same or different? Okay. How about this one? It's hard to hear, I have to admit. So if you do this in laboratory settings, that middle distinction is far easier to hear, because these were all different pairs, by the way. This one, just straddles that categorization boundary between the da and the ta. So this is just a 20 millisecond difference in voice onset time. But most people, again, when you do this in the lab, they will hear that difference. Whereas this difference is much harder to hear, even though it's also associated with just a 20 millisecond difference in voice onset time. That's the key, right? The same differences, they might not be equally perceived as differences. It depends on where those differences fall. If they fall on different sides of a category boundary, then you use your knowledge of what it is that you're hearing to perceive those differences. So what has happened here? There are objective differences in the physical world, right? Voice onset time, that's one way to define the physical world. There are lots of features out there that you can measure. And if some of these differences are, or if some of these stimuli are associated with real things in the world and they fall in different categories, then your perceptual representation might be warped. Where differences within one category, they're minimized. You don't tend to see them as much. Differences between categories, they're maximized. So that's called categorical perception. Is that clear? Now, this is consequences for how we perceive sounds in different languages. So you probably all know that in several Asian languages, or Asian speakers have a trouble distinguishing between the L and the R sounds. Why is that? Well, it's not a meaningful distinction in several Asian languages, although not all. Right? So this is consistent with categorical perception. If for the L and the R in Asian languages, it's like a within category distinction, not as important, those distinctions are minimized. The L and the R in English language is very important distinction, and therefore those differences are maximized. Now it's easy to sort of make fun of other languages and, you know, why can't they understand the difference between L and the R? Because it's so obvious. But let's use an example where some obvious differences in a foreign language, they're very non-obvious to native English speakers. So does anybody speak Hindi here? No? So here are two different sounds, so different phonemes. And let's see if you hear the difference. Let's do it again. Do you hear that? Yeah. Aye. Yeah, most people can hear that, but it's very subtle, right? This is a major distinction in Hindi. And it's associated with a slightly different position of the tongue relative to the tip of your teeth. Now here's one. You don't have to know the details of how these sounds are actually produced. So this is in Salish, a native North American language. And these are some rare consonants that, you know, very few languages produce these kinds of sounds. And I still, to this day, I can't hear any difference between these two. But I'm curious if you can. Does anybody hear a difference? So somebody, a Salish speaker would say, oh, clearly, that's so obvious, right? And the subtle difference, which you don't have to know, and this graph is a little small here, but the back of the tongue can be placed against the velum or against the uvula. Normally we don't do that in English, but that small change in the position of the back of your tongue makes that distinction between the uvular and velar constant, something that we can't hear. So if our higher level knowledge, our knowledge of the native language, if that influences how we perceive that language, so that must mean that at some point in time we actually were able to hear those differences. So as it turns out, infants can hear those distinctions that adults cannot hear. This is one instance where an infant is vastly superior to an adult. They would actually hear those Hindi and Salish differences even when growing up in an English household, at least at some point in time. So the book shows this very nice result. Infants of 6 to 8 months old, so before they start to speak, they can actually distinguish between these Hindi and Salish contrasts. So you do this in a habituation paradigm where you play those sounds, or one of the sounds. The infant gets bored, starts to look away, and then you start to play the other sound, and if they are interested in it again, they start paying attention again, then they clearly can distinguish between those two sounds. So the graph shows that early in infancy, these infants can discriminate between these contrasts, but this distinction is lost over time. Right? So by the time the infant starts speaking, about 1 year of age, that infant already has lost the ability to discriminate between these sounds. And one practical result that comes out of this is that if you want your child to reach native fluency, to be fully understanding and capable of any sort of foreign language or second language, you need to expose your child as early as possible, well before they actually speak the language and start muttering things, to those sound contrasts. Because they will pick up those relevant sound contrasts, and if you don't expose them to them, they might lose the ability to distinguish them. Any questions so far? So I think I'll skip this whole section on semantics, so this will not be part of the test. That's just a small section of the book anyway. And so today, short lecture, and that's it. Thank you.